Picture this: you're standing at the edge of an invisible abyss, where the very fabric of space and time twists into knots. A single step forward, and there's no turning back. The pull is unstoppable, swallowing light itself, warping reality into something unrecognizable. This isn't science fiction, it's the raw, terrifying power of a black hole's event horizon, where gravity doesn't just bend the rules, it rewrites them entirely. And yet, as mind-bending as this sounds, it's just one glimpse into the universe's most extreme gravitational forces, secrets lurking in the cosmos that defy everything we think we know. Gravity is the silent architect of the universe, the force that sculpts galaxies, crushes stars into diamonds, and bends the path of light like a cosmic illusionist. But what happens when gravity isn't just a gentle tug, but a violent, all-consuming monster? Across the cosmos, there are places where gravity doesn't play nice, where it fractures space, slows time to a crawl, and warps matter into forms so bizarre they challenge the limits of human imagination. These are the extremes we're about to explore, places where the laws of physics as we know them start to unravel. Get ready for a journey into the heart of gravity's greatest mysteries. Over the next 30 facts, we'll venture into the crushing depths of neutron stars, where a single teaspoon of material weighs as much as a mountain. We'll witness cosmic collisions so powerful they send ripples through the fabric of spacetime itself, and we'll stare into the abyss of supermassive black holes where time stops and the universe as we know it ceases to make sense. This isn't just a list, it's an expedition into the unknown, a chance to uncover the hidden forces that shape reality itself. So buckle up, we're diving into the extremes. The sun doesn't just light up our days, it's the cosmic glue holding the entire solar system in place. Picture the planets, each locked in an endless dance around this blazing powerhouse, not by choice, but by the sheer force of gravity. Without the sun's immense pull, Earth would drift into the freezing void, and Neptune might vanish into interstellar space like a lost traveler. Its gravity is so dominant that it makes up 99.8% of the solar system's total mass, a literal heavyweight champion keeping everything in check. Even at 93 million miles away, Earth feels the sun's grip every second. To put it in perspective, if you weighed 100 pounds here, standing on the sun's surface, if you could survive its scorching heat, you'd weigh over 2,700 pounds, crushed by gravity 30 times stronger than our own. And it's not just planets feeling the pull. Comets racing in from the outer solar system whip around the sun in hairpin turns, slingshotted by its gravity, while asteroids stranded in the belt between Mars and Jupiter stay trapped, unable to escape this invisible cosmic leash. But here's what's truly mind-blowing. The sun's gravity doesn't just dictate where objects go, it shapes how they move. Planets don't orbit in perfect circles but in elegant ellipses, speeding up as they get closer to the sun and slowing down as they drift away, all thanks to gravity's unbreakable rules. Even light itself bends slightly when passing near the sun, a subtle curve predicted by Einstein and proven during solar eclipses. So next time you feel the warmth on your face, remember, you're not just basking in sunlight. You're experiencing the invisible hand of gravity, the force that built our cosmic neighborhood and keeps it running like clockwork. If you thought the sun's gravity was intense, wait until you hear about neutron stars, the universe's ultimate pressure cookers. These stellar corpses pack more mass than our sun into a city-sized sphere, creating gravitational forces so extreme they distort reality itself. Picture this: a single sugar cube's worth of neutron star material would weigh a staggering 1 billion tons on Earth, heavier than Mount Everest compressed into a tiny speck you could balance on your fingertip. These cosmic anomalies are born from catastrophe. When a massive star explodes in a supernova, its outer layers blast into space while the core collapses inward under unimaginable pressure. Atoms get crushed so violently that electrons merge with protons, leaving behind a dense sea of neutrons packed shoulder to shoulder like sardines in a can. The result, a teaspoon of this neutron soup would contain the mass of every car on Earth combined, an entire planet's worth of matter squeezed into a space smaller than a marble. But here's where things get truly bizarre. The gravity on a neutron star's surface is so strong it bends light into a frenzied dance. If you could stand on one, an impossible feat since you'd be instantly flattened into a thin smear of atoms, you'd see the back of your own head as light curves completely around the star. Time slows to a crawl too. A single second here would pass hours faster for distant observers, and if two neutron stars collide, the resulting gravitational waves ripple through spacetime with enough energy to briefly outshine all the stars in the observable universe combined. These gravitational powerhouses aren't just cosmic curiosities, they're laboratories for physics we can't recreate on Earth. Their crushing density creates states of matter that defy explanation, where atomic nuclei arrange themselves into bizarre shapes known as nuclear poster, twisted into strings and sheets by gravitational forces stronger than anything in our solar system. Some even spin hundreds of times per second, becoming cosmic lighthouses that beam radiation across the galaxy. Yet for all their ferocity, neutron stars have a delicate balance. Add just a bit more mass and they collapse further into black holes. Remove some and they might unravel entirely. They exist on the razor's edge of cosmic extremes, where gravity doesn't just dominate but rewrites the rules of existence itself. Black holes don't just bend space, they twist time itself into knots. Imagine standing near one, close enough to feel its gravitational grip, but not quite close enough to be torn apart. For you, time would crawl like molasses, each second stretching endlessly, while for someone watching from a safe distance, your movements would appear frozen, as if you were trapped in slow motion. This isn't science fiction, it's one of the most mind-bending predictions of Einstein's theory of relativity, where gravity doesn't just pull on objects but warps the very fabric of spacetime. Einstein showed us that time isn't a fixed constant, it's fluid, shaped by gravity's influence. Near a black hole where gravity is unimaginably strong, time slows down dramatically. This effect, called gravitational time dilation, means a clock ticking near a black hole would run far slower than one far away. If you could hover just outside the event horizon, the point of no return, for what felt like minutes to you, years could pass for everyone else in the universe. It's like being stuck in a cosmic time warp where the rules of aging and decay no longer apply evenly. The movie Interstellar brought this concept to life with stunning accuracy. Remember the scene where the crew visits a planet orbiting the supermassive black hole Gargantua. Hours spent on its surface equate to decades passing for their colleague waiting aboard the ship. It's not just Hollywood exaggeration, this is real physics. The closer you get to a black hole's immense gravity well, the more time slows down, a phenomenon confirmed by observations of stars orbiting our galaxy's own supermassive black hole, Sagittarius A. But here's the real kicker. Time dilation isn't just a curiosity, it's a window into the universe's most extreme environments. Black holes push relativity to its limits, revealing how space-time behaves under conditions we can't replicate on Earth. Even GPS satellites orbiting our planet have to account for tiny time distortions caused by Earth's gravity, adjusting their clocks to stay synchronized with the ground. Near a black hole, the effect is so extreme it bends reality itself, turning what we think of as fixed and predictable into something fluid and surreal. This isn't just about clocks running slow, it's about how gravity reshapes existence. If you could peer into a black hole's gravitational grip, you'd see light redshifted into oblivion, stars frozen in time, and the universe itself aging at hyper speed around you. It's a place where the laws of physics as we know them start to unravel, offering clues to mysteries we're only beginning to understand. So the next time you check the clock, remember, time isn't just ticking away. It's bending, stretching, and warping all around us, shaped by the invisible hand of gravity in ways that still leave scientists in awe. The moment an object drifts too close to a black hole, gravity stops playing fair. It becomes a cosmic torture device, stretching and squeezing matter like putty in the hands of a giant. This grotesque transformation has a name: spaghettification. Picture a hapless star or even a hypothetical astronaut approaching the event horizon. The pull on their feet closer to the black hole becomes exponentially stronger than the pull on their head. The difference in gravity's grip stretches them into a thin, noodle-like strand, as if the universe itself were rolling out dough. Long before they're torn apart atom by atom, they'd resemble a piece of spaghetti, hence the term scientists coined to describe this nightmarish process. We actually experience a gentle version of this effect right here on Earth. Our planet's gravity creates tides by tugging more strongly on the side of the oceans nearest to the moon, while the far side feels a weaker pull. That slight difference stretches the water into elongated bulges, giving us high and low tides. But near a black hole, the tidal forces aren't just noticeable, they're catastrophic. The gravitational gradient is so steep that the stretching force over just a few feet would be millions of times stronger than Earth's entire gravitational pull on you. The physics behind this is as elegant as it is brutal. It all comes down to how gravity weakens with distance. On Earth, the difference in gravity between your head and feet is negligible, just a fraction of a percent. But near a black hole, the drop-off is so extreme that the force at your feet could be thousands of times stronger than at your head. The result, your body would be pulled apart like taffy, cells rupturing one by one as molecular bonds snap under the strain. Even a sturdy spaceship wouldn't stand a chance. Metals would shear, electronics would warp, and the entire structure would unravel into a stream of particles spiraling toward oblivion. Astronomers have actually witnessed this in action. In 2019, telescopes caught a star being spaghettified by a supermassive black hole. As it was torn apart, the star's material flared brightly, emitting X-rays that revealed the gruesome process in real time. These tidal disruption events are some of the most violent phenomena in the universe, releasing more energy in weeks than our Sun will over its entire 10 billion-year lifespan. Yet for all their destructive power, these events teach us something profound. The way matter behaves under such extremes gives us clues about gravity's true nature, how it warps space, distorts time, and reshapes everything it touches. Even something as simple as a stretched-out star becomes a cosmic laboratory, revealing secrets about the fundamental forces that govern reality itself. So the next time you see pasta boiling in a pot, remember somewhere out there on the edge of a black hole, the universe is doing something far more terrifying with gravity's invisible hands. At the heart of our Milky Way lurks a silent titan, Sagittarius A, a supermassive black hole with the weight of 4 million suns crushed into a space smaller than our solar system. For decades, this gravitational monster was just a theory, its presence inferred by the frantic orbits of nearby stars whipping around an invisible point at speeds topping 15 million miles per hour. Then, in 2019, humanity got its first real glimpse of the unseen beast when the Event Horizon Telescope captured history. A fiery ring of light framing the black hole's shadow, an image that made headlines worldwide. The discovery didn't come easy. Picture 8 radio telescopes scattered across the globe from Hawaii to the South Pole, synchronized so precisely they functioned as one Earth-sized observatory. Together, they pierced through 26,000 light-years of cosmic dust to reveal the glowing aftermath of spacetime itself being torn apart, that iconic orange ring. That's light bent into a perfect circle by gravity so strong, not even photons can escape its grasp. It's the point where physics as we know it breaks down, a cosmic drain pulling in everything, even time. But Sagittarius A isn't just a destroyer. It's the unseen anchor holding our galaxy together. every star, nebula, and dust cloud in the Milky Way dances to its gravitational tune, slowly circling this invisible pivot like moths around a flame. Without it, our galaxy would lose its structure, spiraling into chaos as stars drifted aimlessly into the void. Even our own solar system, far out in the galactic suburbs, feels its subtle pull as we orbit the center once every 230 million years. What's truly staggering is how quiet this behemoth is. Unlike the violent quasars of the early universe, Sagittarius A sits relatively dormant, only occasionally flaring up when a gas cloud or star strays too close. When it does feed, the show is spectacular material spirals inward at nearly light speed, heating up to millions of degrees and blasting out X-rays detectable across the cosmos. Yet most of the time, it's a sleeping giant, reminding us that even the universe's most extreme forces can operate in eerie silence. The more we learn about this cosmic heavyweight, the stranger it gets. Recent observations suggest it might not be alone. Smaller black holes could orbit it like bees around a queen, creating a gravitational hive mind at the galaxy's core. Some theories even propose it's a gateway, a tunnel through spacetime known as a wormhole, though that remains firmly in the realm of speculation. What's certain is that Sagittarius A holds secrets about how galaxies form, evolve, and perhaps even how they die. So the next time you gaze at the Milky Way's shimmering band across the night sky, remember, you're looking toward a gravitational monarch, a silent ruler whose pull shapes everything you see. Its discovery didn't just confirm a century of astrophysics, it gave us front-row seats to the universe's most extreme forces in action, proving once again that truth is stranger than fiction. And with new telescopes coming online, we're just beginning to unravel the mysteries hidden in its shadow. The universe speaks in whispers, ripples echoing through the fabric of spacetime itself. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, finally tuned in to one of these cosmic murmurs. What they discovered wasn't light or sound, but something far more profound. Gravitational waves radiating from two black holes locked in a death spiral over 1 billion light-years away. Think of tossing a pebble into a still pond, the way rings spread outward in perfect concentric circles. Now imagine that pebble is 36 times the mass of our Sun, and the pond is the very structure of reality. That's the scale of distortion these collisions create, warping spacetime like a funhouse mirror before settling back into stillness. Einstein predicted this phenomenon a century ago, but even he doubted we'd ever detect it. Gravity, he theorized, wasn't just a force, it was the curvature of spacetime by massive objects. When those objects accelerate or collide, they send shockwaves rippling outward at light speed, stretching and compressing space itself as they pass. Picture lying on a trampoline while someone jumps nearby. You'd feel the fabric beneath you wiggle and bend. Gravitational waves do the same to the cosmos, except the trampoline is all of existence, and the jumper might be a pair of black holes merging with the energy of 1 trillion supernovas. LIGO breakthrough detection was a triumph of human ingenuity. Twin observatories in Louisiana and Washington, separated by nearly 2,000 miles, use lasers traveling down 2.5 mile long vacuum tubes to measure distortions smaller than 1/10,000th the width of a proton. When gravitational waves pass through Earth, they briefly squash and stretch space itself, altering the laser's paths by an almost unimaginably tiny amount. That September morning in 2015, both detectors caught the same signal, a distinctive chirp, lasting just 0.2 of a second, representing black holes spiraling together at half the speed of light before merging into one. The numbers behind this event are staggering. In that fraction of a second, the collision converted roughly 3 times the Sun's mass directly into gravitational wave energy, briefly outshining every star in the observable universe combined. Yet by the time those ripples reached Earth over 1 billion years later, They'd weakened so much that the detectors had to filter out local vibrations, passing trucks, distant ocean waves, even raindrops to isolate the signal. It's like trying to hear a pin drop in another galaxy while standing in the middle of a hurricane. Since that first detection, LIGO and its European counterpart Virgo have captured dozens more gravitational wave events, including neutron star collisions that also flared up invisible light. Each detection peels back another layer of cosmic mystery, revealing how often black holes dance together in the dark, how neutron stars shred each other apart, and even hints about the universe's expansion rate. These waves are more than just cosmic curiosities. They're an entirely new way to observe the universe, like gaining a sense we never knew we had. What's truly humbling is how recently we've opened this window. For all of human history, we've studied the cosmos through light, visible, X-ray, radio. Now we're listening to spacetime itself vibrate, catching whispers from collisions that happened before multicellular life existed on Earth. And with new detectors planned for space and upgraded sensitivity on the ground, we're on the verge of hearing even fainter echoes, perhaps from the birth cries of the universe itself, when gravity first shook free from the other fundamental forces. Einstein's math gave us the roadmap, but it took a century of innovation to take that first step into this uncharted frontier. And if history's any guide, the universe still has plenty of surprises left to ripple our way. Imagine crushing the entire mass of the Sun down into a sphere the size of Earth. That's the reality of a white dwarf, one of the universe's most deceptive gravitational powerhouses. These stellar remnants may look small and unassuming, but their gravity is anything but gentle. Step onto the surface of one, if you could survive the 400,000-degree temperatures, and you'd weigh 350,000 times what you do on Earth. A 150-pound person would suddenly feel the crushing weight of 50 million pounds, flattened instantly by forces so extreme they warp the very atoms beneath your feet. White dwarfs are the glowing tombstones of stars like our Sun, what's left after they've burned through their nuclear fuel and shed their outer layers in a dazzling planetary nebula. What remains is a dense, Earth-sized core held up not by nuclear fusion but by quantum mechanics. The electrons in its atoms get packed so tightly they resist further collapse, creating a state called electron degeneracy pressure. It's like trying to cram a stadium's worth of people into an elevator eventually. They push back so hard that not even gravity can squeeze them further. But here's where things get even stranger. As white dwarfs cool over billions of years, their carbon and oxygen cores begin to crystallize, turning into colossal cosmic diamonds. Picture a planet-sized gem slowly solidifying in the cold of space, its lattice structure shaped by unimaginable gravitational pressures. Some of these stellar relics may even have cores of metallic oxygen, a phase of matter so exotic it can't exist naturally anywhere else in the universe. Yet for all their stability, white dwarfs have a dramatic final act. If they steal enough mass from a neighboring star or collide with another white dwarf, they can reignite in a cataclysmic type Ia supernova. These explosions are so precisely uniform in brightness that astronomers use them as cosmic yardsticks to measure distances across the universe. In a matter of seconds, the white dwarf's gravity, once its defining feature, becomes its undoing, triggering a runaway nuclear fusion that obliterates it completely. The legacy of white dwarfs is written across the galaxy. They're the quiet architects of cosmic recycling, spewing heavy elements forged in their cores back into space, where they'll eventually form new stars, planets, and perhaps even life. Our own Sun will one day join their ranks, its light fading into a dense, Earth-sized ember that will glow faintly for trillions of years, a testament to gravity's power to shape not just stars but the destiny of the universe itself. In the darkest corners of the cosmos, beacons of light shine with the brilliance of a trillion suns. These are quasars, the universe's ultimate power plants. At their hearts lie supermassive black holes, but not the quiet giants like Sagittarius A. These are ravenous monsters, devouring entire stars' worth of material every year, and in the process becoming the most luminous objects in existence. The energy they release dwarfs entire galaxies, visible across billions of light years as searing points of light that outshine everything around them. What makes quasars truly extraordinary is the physics behind their glow. As gas, dust, and stars spiral toward the black hole's event horizon, friction heats the material to millions of degrees, creating an accretion disk that shines brighter than any star cluster. Magnetic fields twist this superheated plasma into jets that blast outward at nearly light speed, punching through galaxies and spanning hundreds of thousands of light years. These cosmic searchlights are so intense that some quasars appear brighter than the 1,000 billion stars in their host galaxies combined, all powered by gravity's relentless pull. Their brilliance isn't just a spectacle, it's a time machine. Because light takes time to travel, the farthest quasars we see are snapshots from when the universe was less than 1 billion years old. Their light arrives stretched toward the red end of the spectrum, a phenomenon called redshift that reveals how space itself has expanded during its journey. The most distant quasar known, J0314 plus 0156, beams light from just 670 million years after the Big Bang, its black hole already weighing in at over 1.5 billion solar masses, a cosmic paradox that challenges how such giants could form so quickly. Yet quasars aren't just relics of the past, they're key to understanding how galaxies evolve. Today's dimmer galactic cores, including our own Milky Way, might once have been blazing quasars in their youth. The same gravity that fuels their incredible light also shapes the galaxies around them, heating interstellar gas to prevent runaway star formation and regulating cosmic growth. Some theories even suggest quasar winds blow material into intergalactic space, seeding the universe with the raw ingredients for future stars and planets. What's truly humbling is realizing these distant specks of light aren't stars at all, but the visible signatures of spacetime's most extreme distortions. A quasar's glow comes from the last scream of matter about to vanish forever, a final burst of energy before crossing the point of no return. They remind us that even in the darkest voids, gravity can ignite cosmic fireworks bright enough to illuminate the entire universe, beacons shining across time and space, marking where reality itself bends to its breaking point. Hidden behind the Milky Way's shimmering band of stars, something colossal is pulling thousands of galaxies toward it with irresistible force, an enigma astronomers call the Great Attractor. Picture this: our entire local group of galaxies, including Andromeda and dozens of smaller neighbors, is racing toward this invisible gravitational vortex at over 14 million miles per hour, caught in a cosmic current we still don't fully understand. It's as if the universe has tilted its floor, and everything in our corner of space is sliding toward a drain we can't see. The mystery deepens when you realize why this gravitational monster stayed hidden for so long. Positioned in the constellation Norma, the Great Attractor lies directly behind the Milky Way's dusty central bulge, an area so thick with interstellar debris that visible light can't penetrate. It took cutting-edge X-ray and radio telescopes to peer through this cosmic fog, revealing a concentration of mass so immense it distorts the very fabric of space around it. Current estimates suggest this gravitational behemoth contains the equivalent of 100,000 Milky Ways packed into a region just 600 million light-years across. But what exactly is pulling us in? The leading theory points to the Norma cluster, a dense gathering of galaxies bound together by gravity, plus an even larger structure called the Laniakea supercluster, of which our Milky Way is just a tiny suburb. Imagine standing in a valley surrounded by mountains. Even if you can't see the peaks, you'd feel their mass influencing the landscape. That's how the Great Attractor works. Its gravity warps spacetime on such a scale that entire galaxies flow toward it like rivers down a slope. Recent observations hint there might be something even more mind-bending behind this phenomenon. Some scientists speculate the great attractor could be just the tip of an iceberg, a gravitational shadow cast by something far larger beyond our current observational limits. There's tantalizing evidence of an even more massive structure nicknamed the Shapley attractor, lying 650 million light-years away, which might be the true endpoint of this cosmic river. It's a humbling reminder that what we once thought was the grandest structure in our neighborhood might just be a stepping stone to something incomprehensibly vaster. What's truly astonishing is how this discovery reshaped our cosmic map. Before the Great Attractor's detection in the 1970s, we assumed galaxies were scattered randomly across space. Now we see them moving in coordinated flows, like leaves caught in a gentle breeze, except this breeze is the gravitational fingerprint of structures weighing quadrillions of suns. Even our fastest spacecraft couldn't escape this pull. It's not a force to fight, but a current to ride in the grand ocean of the cosmos. As telescopes grow more powerful, we're peeling back layers of this mystery, revealing how these immense gravitational networks sculpt the universe's large-scale structure. Every new observation suggests that what we've uncovered so far might just be the closest ripple in a pond whose edges we can't yet see. And somewhere in that unexplored darkness, the universe's most extreme gravitational forces continue their silent work, bending the paths of galaxies in ways we're only beginning to comprehend. Stepping onto Mars would feel like stepping into a dream where every movement becomes effortless, yet strangely deceptive. The red planet's gravity, just 38% of Earth's, turns even a simple walk into a buoyant glide. A 180-pound astronaut would suddenly weigh less than 70 pounds, capable of bounding across the rusty terrain with ease. But don't let the lightness fool you. This alien gravity comes with hidden challenges that could make or break humanity's dreams of settling there. Living in Martian gravity isn't just about floating through dust-filled valleys, it's a slow dance with the unknown. On Earth, our bones and muscles constantly fight gravity's pull to stay strong, but on Mars, that resistance nearly vanishes. Without countermeasures, astronauts could lose up to 2% of their bone density per month, their muscles withering like unused rubber bands. Even the heart, no longer working as hard to pump blood against gravity, could weaken over time. This isn't just theory, we've seen it play out on the International Space Station, where microgravity wreaks havoc on the human body despite rigorous exercise routines. Mars offers more gravity than the weightlessness of space, but whether it's enough to prevent long-term deterioration remains one of the biggest unanswered questions for future colonists. The differences between Martian and lunar gravity reveal just how nuanced planetary exploration really is. Jumping on the Moon with its 1/6 Earth gravity sends astronauts soaring several feet high with minimal effort. Remember those iconic Apollo footage bounces. On Mars, that same leap would feel less extreme but more controlled, offering a middle ground between floating and falling. A running stride might cover twice the distance it would on Earth, turning mundane tasks into calculated maneuvers. But this partial gravity also complicates engineering. Spacecraft designed to land on Mars can't rely on the Moon's feather-light touch or Earth's thick atmosphere for braking. Instead, they need a mix of parachutes, retrorockets, and even inflatable heat shields, a balancing act of forces unique to the red planet. Colonizing Mars means adapting to gravity's quiet tyranny in unexpected ways. Picture a child born there. Their body would develop differently, their muscles and bones shaped by a world where carrying heavy loads feels trivial. Returning to Earth might become impossible for them, our home planet's gravity crushing their Martian-adapted frame. Even everyday objects behave differently. Water pours slower, flames burn cooler, and dust hangs in the air longer, all because gravity's weaker grip changes basic physics. Future habitats might need centrifuges to simulate Earth-like conditions, or Martian gyms could feature resistance training tailored to this alien pull. Yet for all its challenges, Mars gravity also offers opportunities. the energy needed to launch rockets from its surface is a fraction of Earth's, potentially making it a stepping stone for deeper space exploration. And its gentle pull could revolutionize industries. Imagine factories producing materials impossible to craft under Earth's stronger gravity, or athletes breaking records in low-gravity sports. The red planet isn't just a destination, it's a laboratory for how gravity shapes life itself. As we prepare to send boots into Martian dust, we're not just solving engineering puzzles, we're rewriting what it means to be human in a universe where gravity isn't constant. Every step, every breath, every heartbeat on Mars will remind us that home isn't just a place. It's a very specific tug between our feet and the ground beneath them, one we're only beginning to understand. Jupiter isn't just the solar system's largest planet. It's our silent guardian, a gravitational shield working tirelessly to protect Earth from cosmic catastrophe. With a mass 2.5 times greater than all other planets combined, its gravity bends the paths of asteroids and comets like a cosmic traffic cop, redirecting potential threats away from our fragile world. Think of it as a celestial vacuum cleaner, its immense pull sucking in or flinging aside debris that might otherwise barrel toward the inner solar system. Without this gas giant standing sentinel, life on Earth would face far more frequent extinction-level impacts, turning Jupiter into the universe's most unlikely hero. The proof of this protective role came crashing down in July 1994, when fragments of comet Shoemaker-Levy 9 struck Jupiter's atmosphere in a fiery spectacle visible from telescopes worldwide. The comet had already been torn apart by Jupiter's gravity during a previous close pass, and now its pieces returned like a cosmic shotgun blast, each impact releasing more energy than all nuclear weapons on Earth combined. Dark scars larger than our planet lingered in Jupiter's clouds for months, stark reminders of what could have happened if those fragments had hit Earth instead. That event wasn't just a light show, it was a live demonstration of Jupiter's gravitational defense system in action. But how exactly does this cosmic vacuuming work? Jupiter's immense gravity creates what scientists call the Kirkwood gaps in the asteroid belt, regions where its repeated tugs destabilize orbits, preventing large asteroids from congregating. Some get ejected from the solar system entirely, while others get slingshotted inward, where Jupiter's gravity often captures or deflects them before they reach us. The math is staggering. Astronomers estimate Jupiter intercepts or redirects up to 99% of long-period comets that might otherwise threaten Earth, a gravitational filtering system operating over billions of years. Yet Jupiter's protection isn't perfect. Its gravity can sometimes perturb objects toward us rather than away, as may have happened with the asteroid that wiped out the dinosaurs. The same forces that clear threats can also create them, like a bouncer who occasionally tosses troublemakers toward the dance floor instead of out the door. This duality makes Jupiter both shield and occasional accomplice, its influence a double-edged sword that reshapes the solar system's danger zones over millennia. Modern simulations reveal an even more fascinating twist. Without Jupiter, Earth might not exist at all. During the solar system's chaotic early days, Jupiter's gravity likely prevented Mars from growing to Earth's size, while also shepherding water-rich asteroids toward our planet. Its gravitational dance with Saturn may have even pushed Uranus and Neptune outward, clearing space for the inner planets to form. Every time you take a breath of air or sip a glass of water, you're experiencing the indirect gifts of Jupiter's gravitational craftsmanship. So the next time you spot Jupiter glowing brightly in the night sky, remember, it's not just another dot of light. It's a gravitational titan, silently steering cosmic bullets away from our pale blue dot. Its storms and swirls masking the most sophisticated planetary defense system we'll ever know. And as we discover more Jupiter-like planets orbiting other stars, we're left wondering how many of them might be protecting alien worlds. Their gravity, the invisible hand that makes life possible elsewhere in the cosmos. Some stars don't just drift peacefully through the galaxy. They're catapulted into the void at speeds that defy comprehension, becoming cosmic fugitives flung by gravity's most violent hands. These hypervelocity stars, racing through space at over 1 million miles per hour, tell a story of gravitational chaos beginning near supermassive black holes. Take HIP 60350, a rogue star clocked at nearly 1.7 million miles per hour, fast enough to cross the continental United States in under 2 seconds. At that speed, it's not merely traveling, it's escaping the Milky Way entirely, destined for the cold emptiness between galaxies. So how does a star become a galactic outcast? The culprit lies in the extreme gravitational dance near our galaxy's central black hole. When a binary star system wanders too close, the black hole's tidal forces can shred the partnership apart. One star gets captured into a tight orbit, while the other is slingshotted outward at unimaginable speeds. It's like cracking a cosmic whip, where gravity doesn't just bend spacetime but weaponizes it, converting orbital energy into raw velocity. The math behind this is staggering. The ejected star can achieve up to 1% of light speed, enough to overcome the Milky Way's gravitational grip forever. HIP 60350 isn't alone. Astronomers have identified dozens of these runaway stars, each carrying forensic evidence of their violent origins. Their trajectories trace back to the galactic center like cosmic breadcrumbs, revealing the black hole's gravitational influence across light years. Some, like S5-HVS1, streak through space so fast they'll leave the galaxy within 100 million years, a blink in cosmic time. Others, slightly slower, become intergalactic nomads, drifting through the void for eons until another galaxy's gravity eventually captures them. The implications of these stellar speedsters stretch far beyond their spectacle. Hypervelocity stars act as celestial probes, their paths helping astronomers map the Milky Way's hidden mass distribution. Since their trajectories depend on the galaxy's gravitational field, tracking them reveals where dark matter clumps and how matter is structured in our cosmic neighborhood. They're also time capsules. By analyzing their composition, scientists can reconstruct conditions near the galactic center millions of years ago when they were flung into exile. Yet the most thrilling possibility lies in what might hitch a ride with them. Planets orbiting hypervelocity stars could theoretically survive the ejection, creating the bizarre scenario of worlds hurtling through intergalactic space, untethered to any star system. Any life on those planets would face an extraordinary fate, watching the Milky Way shrink to a distant smudge as they voyage into the abyss, carried by a gravitational kick so powerful it defies the very structure of the galaxy. These runaway stars remind us that gravity isn't just a force of attraction. It's a sculptor, a slingshot, and sometimes a catapult, capable of launching entire solar systems into the cosmic unknown. They turn the galaxy into a gravitational pinball machine, where the right interaction at the right moment can send a star careening across the universe, forever marked by the moment gravity let go. The moon's gentle tug on our planet does more than paint the night with silver light. It lifts entire oceans in a rhythmic dance that shapes coastlines and ecosystems worldwide. Twice each day, billions of tons of water rise and fall in response to gravity's invisible hand, with the moon pulling harder on Earth's near side than its far side. This difference creates tidal bulges that sweep across the globe, turning beaches into temporary lakes and exposing seafloor mysteries with each retreating wave. But this celestial partnership goes far beyond daily tides. It's slowly putting the brakes on Earth's rotation, stretching our days longer by stealing fractions of a second each century. Locked in this gravitational embrace, Earth and the moon are changing each other in profound ways. Just as the moon raises tides in our oceans, Earth's gravity distorts the moon's crust, creating moonquakes that ripple through its rocky surface. This energy exchange comes at a cost. Earth's rotation loses angular momentum, transferring it to the moon's orbit. The result, our days grow imperceptibly longer while the moon spirals outward at about 1.5 inches per year, the cosmic equivalent of a slowing top extending its arms. Fossilized tidal patterns in ancient sedimentary rocks reveal this gradual shift. 400 million years ago, a day lasted just 22 hours, and a year contained nearly 400 of these shorter days. This process, called tidal locking, has already shaped the moon's rotation into perfect sync with its orbit, one reason we only ever see one face of our celestial neighbor. Given enough time, Earth would eventually become tidally locked to the moon too, with one hemisphere permanently moonlit while the other faced eternal darkness. But before that happens, the sun's expansion into a red giant will likely consume both worlds in about 5 billion years. Until then, the dance continues. Each high tide acts as a subtle brake pad against Earth's rotation, while the drifting moon carries away stolen energy like a cosmic thief. Future projections paint an intriguing picture. In another 50 billion years, should Earth somehow survive the sun's death throes, our planet's rotation would slow to match the moon's orbital period, creating a 47-day-long day where one side of Earth always faces the moon. Coastal cities would experience permanent high tides on the lunar side and permanent low tides opposite, radically reshaping ocean currents and climates. Meanwhile, the moon's distance would stabilize at about 1.5 times its current remove, appearing smaller in the sky but still wielding gravitational influence. This slow-motion ballet between worlds reminds us that gravity's effects accumulate over timescales beyond human comprehension. What feels like a gentle pull today writes destiny across geological epochs, proving that even the weakest fundamental force can move mountains given enough time. So the next time you watch the tide roll in, remember, you're witnessing the universe's most patient dance, one that's been choreographed over 4 billion years and will continue long after humanity's curtain call. Venus is Earth's twisted sister, a world where gravity feels almost familiar, but everything else is a nightmare. Step onto its surface and your weight would barely change, the planet's gravity just 9% weaker than Earth's. Yet that's where the similarities end. Beneath a crushing atmosphere 92 times denser than ours, where the air itself acts like an ocean of superheated acid, Venus proves that gravity alone doesn't make a world habitable. What makes this gravitational twin so inhospitable? The answer lies in its geologic heart. While Earth's surface constantly recycles itself through plate tectonics, a process that regulates our climate by trapping carbon in rocks, Venus chose a different path. Its crust is a single, unbroken plate, a planetary pressure cooker where heat and gases build up with no release valve. Instead of gradual tectonic shifts, Venus experiences catastrophic resurfacing events where pent-up energy erupts in planet-wide volcanic cataclysms. Imagine Earth's most violent supervolcanoes, but occurring everywhere at once, spewing enough lava to drown entire continents in molten rock. These apocalyptic eruptions pump the atmosphere full of greenhouse gases, creating a runaway effect that bakes the surface at 880 degrees Fahrenheit hot enough to melt lead. The contrast between these sibling worlds couldn't be starker. Earth's gravity helps maintain our protective magnetic field, generated by a churning metallic core. Venus, rotating too slowly to produce the same dynamo effect, lost its magnetic shield eons ago. Solar winds stripped away its water, leaving behind a desiccated wasteland where the only rain is sulfuric acid. Yet despite this brutality, Venus's gravity still holds onto an atmosphere thicker than Earth's, proving that a planet's pull doesn't guarantee balance, only the raw force of retention. Space missions reveal even stranger quirks. Soviet Venera landers transmitted haunting images of Venus's rocky plains before succumbing to the heat and pressure within hours. Their data showed landscapes shaped by gravity similar to Earth's, yet utterly alien volcanic domes the size of Alaska, fractured plains that stretch for thousands of miles, and winds that howl at walking speed despite the thick air's resistance. Even the planet's highland regions, which should be cooler, are smothered under the same lethal blanket, proving that gravity's gentle similarity offers no refuge from atmospheric insanity. Scientists suspect Venus wasn't always this way. Billions of years ago, it may have had oceans and temperate climates, its gravity potentially nurturing conditions not unlike early Earth. But somewhere along the way, a subtle divergence, perhaps the lack of a moon to stabilize its tilt or slightly more sunlight, triggered an irreversible chain reaction. The same gravity that makes Venus feel eerily Earth-like became an accomplice to its ruin, trapping heat and toxic gases in a self-perpetuating cycle. This paradox makes Venus a warning and a wonder. It teaches us that gravity is just one ingredient in the cosmic recipe for life too weak, and a planet can't hold an atmosphere too strong, and it might trap deadly extremes. Venus sits in the Goldilocks zone for gravitational similarity, yet everything else went catastrophically wrong. As we search for Earth-like worlds orbiting distant stars, Venus stands as a reminder. Even with the right gravity, a planet's destiny depends on a fragile interplay of forces we're only beginning to understand. Galaxies spin like cosmic carousels, their stars whirling at speeds that should fling them into the void, yet something invisible keeps them tethered. This cosmic glue, known as dark matter, exerts gravitational influence without emitting or reflecting light, hiding in plain sight while shaping the universe's largest structures. Picture a spiderweb you can't see, its delicate threads holding entire galaxies together despite their dizzying rotations. Without this mysterious substance, the Milky Way would have unraveled eons ago, its stars scattered like marbles across the emptiness of space. The first clues to dark matter's existence came from observations that defied explanation. In the 1930s, astronomer Fritz Zwicky noticed something bizarre about the Coma cluster, a group of galaxies moving so fast that their visible mass couldn't possibly generate enough gravity to keep them bound. He called the missing ingredient Dunkel Materie, or dark matter, a placeholder for an enigma we're still unraveling today. Decades later, Vera Rubin's studies of spiral galaxies confirmed the puzzle. Stars at the edges orbited just as quickly as those near the center, violating Newton's laws unless invisible mass was propping up the system. Modern estimates suggest dark matter outweighs ordinary matter 5 to 1. Woven through every galaxy and stretching across the cosmos in vast, intricate filaments. Its gravity sculpts the universe's large-scale structure, guiding galaxies into clusters and superclusters along invisible highways. Yet despite its dominance, dark matter remains elusive. It doesn't interact with light or ordinary matter except through gravity, making it the ultimate cosmic ghost felt but never seen. Scientists have devised ingenious methods to hunt this phantom. Massive detectors buried deep underground wait for the rare moment a dark matter particle bumps into an atomic nucleus, while space telescopes map its distribution by observing how its gravity bends light from distant galaxies. Even the Large Hadron Collider smashes particles at near-light speeds, hoping to create dark matter in conditions reminiscent of the early universe. Some theories suggest it could be made of weakly interacting massive particles, or WIMP, while others propose exotic actions or even primordial black holes formed in the Big Bang's aftermath. The search takes on new urgency as contradictions emerge. Certain dwarf galaxies appear to have less dark matter than predicted, while others seem to have none at all. Observations that challenge our models. Some researchers speculate dark matter might interact with itself through unknown forces, or that our understanding of gravity needs revising entirely. What's certain is that dark matter's gravitational handiwork surrounds us. Every time you look at the night sky, you're seeing stars held in place by an invisible scaffold, a cosmic skeleton we've only begun to trace. Unlocking its secrets won't just explain why galaxies stay intact, it could rewrite our understanding of the universe's very fabric. the universe is caught in an epic tug of war, with gravity desperately clutching galaxies together while an invisible force rips them apart. This cosmic struggle is measured by the Hubble constant, a number so fundamental it could tell us the fate of everything. Picture two galaxies drifting away from each other like boats on an expanding river. For every 3 million light-years between them, space itself stretches another 70 kilometers every second. That's the current best estimate of how fast the universe is growing, a rate first glimpsed by Edwin Hubble in 1929 when he noticed distant galaxies all racing away from us, their light stretched redder the farther they were. But here's where things get messy. Despite a century of research, scientists still can't agree on the Hubble constant's exact value. Some measurements using distant supernovas suggest expansion is faster than estimates based on the cosmic microwave background, the afterglow of the Big Bang. The difference might seem small, 70 versus 74 kilometers per second per megaparsec, but in cosmic terms, it's a screaming alarm that we're missing something fundamental about how gravity and dark energy interact. The implications are staggering. If expansion is faster than predicted, it could mean dark energy. The mysterious force accelerating the universe's growth is stronger over time. Alternatively, gravity might weaken across vast distances, or unknown particles are tweaking the cosmos's expansion history. Some theories even suggest our universe collided with another bubble universe in the distant past, leaving behind ripples that skewed the measurements. The Hubble constant isn't just a number, it's a battlefield where our best theories about gravity and the universe's structure are being tested. Observatories like the Hubble Space Telescope and the upcoming Nancy Grace Roman Telescope are racing to settle the debate. Their mission measured distances to celestial objects with unprecedented precision, from pulsating stars called Cepheid variables to the flicker of distant quasars. Each new measurement is a snapshot of the universe's expansion at different epochs, letting us piece together how dark energy's push has changed against gravity's pull over billions of years. What's truly humbling is realizing this expansion isn't something happening in space. It's space itself stretching. Gravity binds galaxies and clusters locally, but on cosmic scales, dark energy wins, carrying galaxies away so fast that light from some will never reach us in the future. The Hubble constant is more than a speedometer for the cosmos. It's a countdown clock, ticking toward a future where distant galaxies vanish beyond an unreachable horizon, leaving only our gravitationally bound neighborhood visible in an otherwise empty void. And yet, even as gravity loses the war, it still shapes the universe's structure in ways we're only beginning to map. Mercury stands as a cautionary tale of gravity's limits, a world so close to the Sun that its feeble gravitational grip can't even cling to an atmosphere. At just 38% of Earth's gravity, the smallest planet in our solar system is constantly being stripped bare by solar winds, its surface blasted into a barren wasteland where gas molecules escape into space faster than the planet can recapture them. Imagine trying to hold water in a sieve while standing in a hurricane. That's Mercury's losing battle against the Sun's relentless outflow of charged particles. The numbers tell a sobering story. While Mars, with similarly weak gravity, at least retains a thin atmosphere, Mercury's air pressure is 1 trillion times less than Earth. What little gas exists comes from temporary sources, atoms blasted off its surface by micrometeorite impacts, or sodium and oxygen particles weakly clinging to its rocky exterior like dew on a windshield. Even these tenuous coatings don't last. The Sun's radiation accelerates them to escape velocity within days, leaving Mercury as airless as the Moon despite being larger and more massive. Compare this to Venus, where gravity 91% of Earth's has allowed the planet to hoard an atmosphere 90 times thicker than ours, a toxic blanket that creates crushing surface pressures. Or Mars, where 38% gravity, identical to Mercury's, still manages to retain enough carbon dioxide for polar ice caps and seasonal winds. The difference lies in distance and magnetism. Mercury's proximity to the Sun subjects it to solar winds 10 times stronger than what Mars endures, while its lack of a global magnetic field leaves its atmosphere defenseless against this cosmic sandblaster. Recent discoveries by NASA, a messenger probe, revealed gravity isn't Mercury's only weakness. The planet's extreme temperature swings from 800 degrees Fahrenheit during the day to -290 at night to create thermal escape, where heated gas molecules gain enough energy to break free from gravity's grasp entirely. It's a 1-2 punch of solar battering and thermal evaporation that ensures Mercury remains perpetually naked under the cosmic elements. Yet for all its atmospheric poverty, Mercury holds lessons about how gravity shapes planetary destiny. Its surface bears scars of a violent past where it may have been larger before colossal impacts stripped away much of its outer layers. Had it formed farther from the Sun or retained a magnetic field like Earth's, its gravity might have been enough to nurture at least a transient atmosphere. Instead, it serves as a stark reminder that gravity alone isn't enough. Location, protection, and cosmic luck all play their parts in whether a world becomes a life-bearing oasis or a scorched, airless rock spinning silently through space. Einstein's theory of relativity predicted something extraordinary. Gravity doesn't just pull on objects, it bends the very fabric of space and time, twisting the path of light itself. This phenomenon, called gravitational lensing, turns massive cosmic objects into natural telescopes, magnifying and warping the light of galaxies billions of light years behind them. Picture holding a magnifying glass over a newspaper, except instead of glass, it's an entire galaxy cluster, and instead of words, you're glimpsing the distant universe in ways no human-made telescope could ever achieve. One of the most striking examples of this cosmic illusion is Einstein's cross, a quasar 5 billion light-years away whose light gets split into 4 distinct images as it passes through a foreground galaxy. The galaxy's gravity curves spacetime so dramatically that the quasar's light takes multiple paths around it, like a fork in a cosmic highway where each route reaches us at slightly different times. This isn't just a visual curiosity, it's proof that gravity reshapes our view of the universe, revealing objects otherwise hidden in the void. Galaxy clusters weighing as much as a quadrillion suns amplify this effect to staggering extremes. The Hubble Space Telescope's Frontier Fields project used clusters like Abell 1688 as natural zoom lenses, revealing galaxies so faint they'd be invisible otherwise. The light from these ancient objects gets stretched and contorted into luminous arcs and smears, like reflections in a funhouse mirror. Some appear multiple times in the same image, their light bent around the cluster's dense core like water flowing around a boulder. What makes gravitational lensing so powerful is its unintentional side effect. It lets us map the invisible. By analyzing how background light gets distorted, astronomers can trace the distribution of dark matter within the lensing cluster, unveiling the hidden scaffolding that holds galaxies together. Sometimes the lens reveals objects we didn't even know to look for, like MAX 0647 JD, one of the most distant galaxies ever observed, its light amplified 30 times by a fortuitously aligned cluster. The math behind this cosmic trickery is just as mind-bending as the images. Einstein's equations show that the amount of light bending depends on how closely the background object, the lens, and Earth align. Perfect alignment creates a full Einstein ring, a halo of light encircling the lensing galaxy, while slight offsets produce those iconic crosses and arcs. Modern sky surveys now spot thousands of these gravitational mirages, each one a testament to gravity's power to distort reality itself. Beyond pretty pictures, gravitational lenses are rewriting astronomy's playbook. They've helped measure the universe's expansion rate independently of other methods, weighed supermassive black holes, and even hinted at the nature of dark energy. The next generation of telescopes, like the James Webb Space Telescope and the Vera C, Rubin Observatory will exploit this phenomenon to peer further back in time than ever before, capturing the faint glow of the universe's first galaxies stretched and magnified by the gravity of cosmic giants. So the next time you see those shimmering arcs in a telescope image, remember, you're not just looking at warped light. You're witnessing gravity's signature on the cosmos, a reminder that even emptiness isn't truly empty, but a dynamic stage where mass and light dance to the universe's most fundamental tune. The Milky Way isn't floating alone in the cosmic void. It's locked in a gravitational embrace with our closest galactic neighbor, Andromeda, and this dance will end in a spectacular collision. 4 billion years from now, these two titans of our local universe will merge in a slow-motion cataclysm that reshapes both galaxies forever. Right now, Andromeda barrels toward us at 250,000 miles per hour, drawn inexorably by gravity's pull. But don't brace for impact. Cosmic timescales turn even violent mergers into a graceful ballet spanning hundreds of millions of years. Simulations of this event reveal a breathtaking sequence. As Andromeda approaches, its gravity will stretch the Milky Way's spiral arms like taffy, warping the familiar disk we see today. Stars won't physically collide, the distances between them are too vast, but their orbits will be flung into chaos. Some will be ejected into intergalactic space, while others will spiral toward newly forming galactic cores. The night sky for any surviving civilizations would transform radically. Instead of a band of Milky Way stars, observers would see Andromeda looming larger each century until it fills half the sky with its 100 billion stars. A climax comes when the galaxy's supermassive black holes, each weighing millions of suns, begin circling each other in a deadly gravitational tango. As they lose energy through gravitational waves, their orbits tighten until they finally merge in an eruption of spacetime ripples visible across the universe. This collision will unleash enough energy to briefly outshine all the stars in the new galaxy combined, sending shockwaves through remaining gas clouds and triggering waves of new star formation. What emerges from this cosmic car crash won't resemble either original galaxy. Simulations suggest the merger will forge a giant elliptical galaxy nicknamed Milkdromeda, its stars orbiting in random directions rather than the orderly spirals we know today. The new galaxy's core will blaze with the combined light of aging stars, while its outer reaches will be strewn with stellar refugees, suns flung far from their birthplaces during the chaos. Yet for all the violence, this merger is part of a natural cycle. Galaxy collisions were far more common in the early universe, and they're key to how galaxies grow. Our own Milky Way bears scars of past mergers, streams of stars ripped from smaller galaxies it has cannibalized over billions of years. The difference is scale. When two giants like Andromeda and the Milky Way collide, it's not just a meal, it's the creation of something entirely new. The irony is profound. Gravity, the same force that holds planets in orbit and keeps our feet on the ground, will one day dismantle the galaxy we call home and rebuild it into something unrecognizable. Yet even in this distant future, gravity will still govern the motions of stars and planets, proving that while galaxies may change, the underlying laws of the universe remain constant. So next time you gaze at Andromeda's faint smudge in the night sky, remember, you're looking at our galaxy's future, a slow-motion reunion written in the language of gravity. Saturn's rings don't just float in space, they're sculpted by an invisible hand, their delicate strands held in perfect balance by gravity's precise touch. While the planet's surface gravity clocks in at just 1.06 times Earth's, meaning you'd barely feel heavier standing there, its influence extends far beyond its cloud tops, orchestrating the most intricate ring system in the solar system. These icy bands, some no thicker than a skyscraper is tall, stretch over 280,000 kilometers across yet remain sharply defined, their edges crisp as if drawn by a cosmic razor. The secret to this precision, a celestial ballet between Saturn's gravity and tiny moons hidden within the rings themselves, Take Pan and Daphnis, two of Saturn's shepherd moons. These small, potato-shaped worlds orbit within gaps in the rings, their gravity clearing paths like snowplows through a blizzard. As they move, their pull tugs on nearby ice particles, sculpting the edges of the gaps into rippling waves. Some of these disturbances rise several kilometers high, visible proof of gravity's light but persistent touch on even the smallest scales. Other moons, like Prometheus and Pandora, work in tandem, their gravitational nudges confining the F-ring into a tight, braided strand no more than 100 kilometers wide. Without these shepherds, Saturn's rings would have spread into a featureless disk billions of years ago, their particles scattered by collisions and radiation. But gravity's artistry doesn't stop there. Orbital resonances, where a moon's gravitational tugs sync up with ring particles at regular intervals, create some of the system's most stunning patterns. Mimas, the moon responsible for the colossal Cassini division, a gap wider than the distance between Earth and the moon, exerts its pull every time ring particles orbit twice. This repeated nudge acts like a metronome, ejecting particles from the zone entirely. Elsewhere, resonances with other moons generate spiral density waves, curling through the rings like grooves in a vinyl record, each one a frozen snapshot of gravitational harmony. The contrast with Earth's gravity couldn't be starker. Our planet's stronger pull quickly drags down any orbiting debris, which is why we don't have permanent rings of our own. Saturn's weaker gravity, combined with its greater distance from the Sun, allows ice particles to persist in orbit for eons. Yet even Saturn's rings are ephemeral. NASA, a Cassini mission revealed they're likely no more than 100 million years old, a blink in cosmic time. Material rains down onto the planet at an Olympic-sized swimming pool's worth every day, meaning these iconic bands are both a masterpiece of gravitational engineering and a fleeting phenomenon. What's truly remarkable is how much these delicate structures reveal about gravity's versatility. The same force that anchors us to the ground and keeps planets in their orbits also crafts ethereal beauty on scales both vast and minute. Saturn's rings are more than just decoration, they're a dynamic laboratory, demonstrating how gravity shapes order from chaos, one particle at a time. As we study their intricate patterns, we're glimpsing the universal principles that sculpt not just planets and moons, but entire galaxies across the cosmos. At the heart of a black hole lies a place where gravity stops playing by the rules, the singularity, a point where density becomes infinite and all known laws of physics crumble. Imagine squeezing the entire mass of a star or even a galaxy into a space smaller than an atom, a dot so dense that not even the subatomic particles within it can resist being crushed together. Here, gravity doesn't just dominate, it becomes infinite, warping spacetime into a knot so tight that even Einstein's equations fail to describe it. The math behind singularities is as elegant as it is terrifying. General relativity predicts that once matter crosses a black hole's event horizon, there's no force in the universe strong enough to prevent its collapse into a single, dimensionless point. Space and time swap roles. Falling forward isn't a choice but an inevitability, with every possible path leading toward the center. At the singularity itself, curvature becomes infinite, tidal forces grow without limit, and our understanding of reality simply stops. It's not just that we don't know what happens there, the tools we use to describe the universe literally cannot function under such conditions. Yet nature abhors absolute extremes, and quantum mechanics offers a potential escape hatch: Hawking radiation. Stephen Hawking's groundbreaking work revealed that black holes aren't entirely black. They can slowly evaporate by emitting particles at their edges. Quantum fluctuations near the event horizon allow pairs of virtual particles to appear, with one falling in while the other escapes, carrying away energy. Over trillions of years, this process could cause a black hole to lose mass and eventually vanish, leaving behind only a faint whisper of radiation. The catch: Hawking radiation doesn't resolve the singularity itself. It merely provides a way for black holes to decay from the outside in. The infinite gravity at the core remains untouched by this quantum leakage, meaning we're still left with a fundamental contradiction: general relativity's prediction of a singularity versus quantum mechanics' insistence that infinite densities can't exist. Reconciling these two theories is one of physics' greatest challenges, a puzzle that may require a theory of quantum gravity to solve. Some scientists speculate singularities might be replaced by something less extreme, a Planck star, or a dense, exotic state of matter governed by quantum effects. Others propose the black hole's interior doesn't lead to a point at all, but tunnels into another universe or branches into a holographic projection of information on the event horizon. Each theory offers a different escape from infinity, but none have been proven. What's clear is that singularities mark the frontier of human knowledge, where our best theories collide and shatter. They're reminders that gravity, for all its power, is still hiding its deepest secrets, places where the universe folds in on itself, leaving us to wonder what lies beyond the edge of understanding. Earth's gravity might feel constant beneath your feet, but it's actually a patchwork of invisible highs and lows sculpted by mountains, ocean trenches, and even pockets of dense rock deep underground. These variations are too subtle for us to notice. A person weighing 150 pounds in the Himalayas might only gain or lose a fraction of an ounce compared to their weight at sea level, but they reveal the planet's hidden structure in astonishing detail. NASA twin GRACE satellites have been mapping these gravitational nuances since 2002, orbiting in tandem like cosmic detectives to measure how Earth's mass distribution shifts over time. The secret to their precision lies in their dance. Flying 220 kilometers apart, these satellites constantly measure the microscopic changes in distance between them using microwave signals accurate to within 1 micron, about the width of a red blood cell. When the lead satellite passes over an area with slightly stronger gravity, say an underwater mountain range, it gets pulled forward, momentarily widening the gap before the trailing satellite catches up. Over weaker zones like the deep Mariana Trench, both spacecraft dip slightly, revealing regions where Earth's gravitational grip relaxes by fractions of a percent. What emerges from this data is a gravity map of unprecedented detail. The Andes Mountains, buoyed by thick continental crust, create a noticeable upward tug, while the vast underground reservoirs of the Amazon basin appear as subtle dimples in the planet's gravitational field. Even long-buried geological features, like the dense remnants of ancient tectonic plates sinking into the mantle, leave fingerprints detectable by GRACE-sensitive instruments. But these satellites do more than just chart static landscapes. They capture Earth in motion. Seasonal water shifts, like the monsoon rains flooding India or the snowpack melting in the Rockies, appear as rippling changes in local gravity. When California's Central Valley farmers pump groundwater during droughts, GRACE detects the sudden loss of mass as aquifers empty. The satellites have even tracked the slow rebound of land once crushed by ice sheets during the last glaciation, like a memory foam mattress rising after you've stood up. These variations aren't just academic curiosities, they're vital tools for understanding our planet. By combining gravity maps with other data, scientists can predict earthquake risks along subduction zones, locate untapped mineral deposits, and monitor polar ice loss with precision. GRACE successors, like the GRACE-FO mission, now track these changes in near real time, offering early warnings for droughts and floods by sensing water's gravitational whisper before the first cloud appears. So the next time you feel grounded by Earth's pull, remember gravity isn't a monolithic force. It's a living, breathing signature of our planet's shape and substance, constantly reshaped by everything from tectonic collisions to the shifting weight of raindrops. And thanks to these orbiting sentinels, we're learning to read its subtle language like never before. Far beyond the orbits of Neptune and Pluto, in the frozen darkness where sunlight fades to a faint glimmer, lies a spherical shell of icy debris stretching nearly a light year into space, the Oort cloud. This distant frontier marks the true edge of our solar system, where the Sun's gravity, weakened by unimaginable distance, still maintains its faintest grasp. Imagine a cosmic net cast so wide that its strands are nearly invisible, yet strong enough to hold trillions of icy bodies in loose orbits, some destined to become the comets that occasionally streak through our inner solar system. At this staggering distance, the Sun appears as little more than an exceptionally bright star, its gravitational influence reduced to a whisper. A hypothetical observer floating here would experience gravity millions of times weaker than on Earth, so feeble that a gentle push could send an object drifting away forever. Yet over eons, this tenuous pull adds up. The Oort cloud's icy inhabitants, some as large as mountains, move so slowly that their orbital periods can span millions of years, tracing lazy elliptical paths that bring them briefly inward before the Sun's weak tug guides them back to the cold outer darkness. What's astonishing is how this delicate balance shapes our solar system story. Long-period comets like Hale-Bopp, whose brilliant tails lit up Earth's skies for months, originate here, their journeys beginning when passing stars or galactic tides nudge them slightly off course, sending them falling sunward like marbles rolling down a shallow slope. These icy wanderers are fossils from the solar system's birth, preserved in deep freeze for billions of years, only to flare into visibility when a gravitational nudge sends them spiraling toward the inner solar system. The scale of this structure defies comprehension. If you shrank the solar system so that Neptune's orbit fit inside a coffee cup, the Oort cloud would extend beyond a football field. Some estimates suggest its outer edge brushes against the gravitational influence of nearby stars, creating a blurred boundary where the Sun's dominance fades into the Milky Way's collective pull. Yet even here, our star's gravity persists, a testament to its reach across cosmic distances. This fragile arrangement reveals gravity's hidden patience. Unlike the violent extremes near black holes or neutron stars, the Oort cloud showcases gravity's gentle, cumulative power, a force content to work over timescales longer than human history, shaping the cosmos not through brute strength but through persistence. It's a reminder that even the faintest gravitational whisper, given enough time, can orchestrate the grandest of celestial ballets. Gravity isn't just an anchor tethering planets to their orbits, it's also the ultimate cosmic slingshot, capable of flinging spacecraft across the solar system without a drop of fuel. NASA engineers have mastered this art of gravitational theft, turning planets into celestial catapults that boost probes to speeds impossible through propulsion alone. The Voyager missions pulled off this trick with breathtaking precision, using Jupiter's immense gravity to gain nearly 20,000 miles per hour in free acceleration, a maneuver that turned what should have been a 30-year journey to Saturn into just 4. The physics behind these gravity assists is deceptively simple. As a spacecraft approaches a planet, it falls into its gravitational well, gaining speed like a roller coaster plunging down a hill. But unlike a roller coaster, the spacecraft doesn't return all that energy climbing back out instead. It steals a tiny fraction of the planet's orbital momentum, altering its trajectory and velocity relative to the Sun. Think of it like bouncing a tennis ball off a moving truck. If timed right, the ball rebounds with extra energy borrowed from the truck's motion. Jupiter, orbiting the Sun at 29,000 miles per hour, makes an ideal truck for this cosmic trick shot. Voyager's trajectory planners didn't just rely on luck, they wielded Newton's laws like a conductor's baton. By carefully calculating approach angles down to hundredths of a degree, they ensured the spacecraft swung behind Jupiter's direction of orbit, allowing the planet's gravity to drag it forward like a surfer catching a wave. The math reveals the elegance. Voyager 1 entered Jupiter's sphere of influence at about 35,000 miles per hour relative to the planet, but left at nearly the same speed in a new direction, a change that translated to a massive velocity boost relative to the Sun. This technique isn't limited to Jupiter. The Cassini mission performed no fewer than 4 gravity assists, 2 from Venus, 1 from Earth, and 1 from Jupiter before reaching Saturn. Each flyby acted as a stepping stone, incrementally stretching the spacecraft's orbit until it could rendezvous with the ringed planet. Even tiny Mercury has been used as a gravitational springboard, with NASA, a messenger probe, executing 3 flybys to shed enough speed to enter orbit around the scorched world, a maneuver as delicate as using a series of gentle taps to slow a rolling billiard ball. Modern missions have pushed gravity assists to new extremes. The Parker Solar Probe will shatter speed records by performing 7 Venus flybys to inch closer to the Sun, each maneuver trading orbital height for mind-bending velocity. Unlike earlier missions that mainly gained speed, Parker's assists are carefully designed decelerations like a skydiver, using updrafts to control their descent, allowing it to resist the Sun's pull and study our star's corona at distances previously thought impossible. What's truly remarkable is how these maneuvers reveal gravity's dual nature, both tether and catapult, prison and escape route. The same force that keeps planets in their orbits becomes the key to breaking free from them, proving that even the universe's most fundamental laws can be harnessed, redirected, and yes, sometimes even stolen. Gravity's influence doesn't stop at planets or galaxies. It weaves the universe's largest structures into existence, sculpting cosmic webs so vast they defy comprehension. The Sloan Great Wall, a filament of galaxies stretching 1.4 billion light-years across, stands as one of gravity's most stunning masterpieces. Picture a thread of glittering cities suspended in darkness, each city an entire galaxy, bound together by invisible strands of gravitational attraction. This isn't just a random scattering of stars, it's proof that gravity operates on scales almost too large to grasp, organizing matter into patterns that resemble neurons in a cosmic brain. These galaxy filaments trace the universe's underlying skeleton, with gravity pulling matter into dense ribbons separated by unimaginably empty voids. The geometry is mind-bending. The filaments themselves are only 20 to 50 million light-years thick, yet they stretch hundreds of millions of light-years long, forming the borders between emptiness so vast it could swallow thousands of Milky Ways whole. In the Boötes void, one such desert of space spans 330 million light-years with barely 60 galaxies drifting in its expanse, a region so underpopulated that if our Milky Way sat at its center, we wouldn't have discovered other galaxies until the 1960s. What's astonishing is how recently we've mapped this architecture. The Sloan Digital Sky Survey, which revealed the Great Wall in 2003, exposed just how much we'd underestimated gravity's reach. By painstakingly charting millions of galaxies, astronomers realized these filaments weren't anomalies, they were the universe's default structure, shaped over billions of years as gravity amplified tiny density fluctuations left over from the Big Bang. Dark matter plays a crucial role, its invisible gravitational scaffolding guiding ordinary matter into these sprawling cosmic highways. The dynamics at work are as beautiful as they are complex. Imagine dropping blue dye into a still pond initially. It spreads evenly, but tiny currents soon concentrate it into intricate patterns. The universe's matter behaves similarly, with gravity acting as the current. Regions slightly denser than their surroundings pulled in more material over eons, growing into knots where galaxies cluster, while emptier zones became voids. The result is a three-dimensional tapestry where galaxies align along filaments like dew clinging to a spider's web, with galaxy clusters marking the intersections like glittering jewels. Yet even these colossi have limits. The Great Wall's size flirted with cosmological principle, the idea that the universe should look roughly the same everywhere at large scales. Some researchers initially questioned whether such a structure could form under known physics, but supercomputer simulations confirmed gravity could indeed craft these titanic networks given enough time. Newer surveys have revealed even larger candidates, like the Hercules Corona Borealis Great Wall, spanning 10 billion light-years, a potential challenge to our understanding of cosmic evolution. What's humbling is realizing we're not just observers of this grand design, we're embedded within it. The Milky Way resides in the Laniakea supercluster, a filament-connected sprawl of 100,000 galaxies, all drifting toward the same gravitational focal point. Every star we see, every planet we explore, exists because gravity patiently sculpted chaos into structure, transforming a uniform cosmic soup into the intricate web we now call home. And as telescopes peer deeper into the abyss, they reveal this pattern repeating across billions of light-years. Gravity's signature written large in filaments and voids older than time itself. Deep beneath the chaos of our everyday world, scientists are tuning into whispers from the dawn of time, gravitational waves so ancient they might carry echoes from the universe's first trillionth of a trillionth of a trillionth of a second. These aren't the space-time ripples from black hole collisions we've detected before, but something far more elusive, primordial gravitational waves, theorized to have been etched into the cosmos during a violent growth spurt called inflation, when the entire universe expanded faster than light itself. Finding them would be like discovering the cosmic equivalent of a dinosaur's heartbeat, a direct signal from the moment gravity first shook free from the other fundamental forces. Future observatories like the Laser Interferometer Space Antenna LISA and the Cosmic Explorer aim to listen for these faint tremors with sensitivity beyond anything we've built before. Picture 3 spacecraft floating 2.5 million kilometers apart, firing lasers to measure distortions smaller than an atom's width across, a ruler precise enough to catch spacetime's earliest shivers. These waves wouldn't come from colliding black holes, but from the universe's very fabric being stretched during inflation, a process that might have left spacetime itself ringing like a struck gong. If detected, their patterns could reveal whether inflation truly happened, how hot the Big Bang was, or even if our universe is just one bubble in an infinite multiverse froth. The implications border on philosophy. Some theories suggest these waves could carry imprints of other universes brushing against ours during inflation, their gravitational fingerprints lingering in the ripples. Others propose the waves might show evidence of extra dimensions, tiny, curled-up folds in reality where gravity leaks between branes of existence. The wildest ideas speculate that primordial waves could encode the universe's ultimate fate, whether it will expand forever, collapse back into a singularity, or tear itself apart in a big rip. Yet the challenge is staggering. These waves, if they exist, have been stretched by 14 billion years of cosmic expansion, their wavelengths now potentially as wide as the observable universe. Distinguishing them from noise requires isolating vibrations a billion times fainter than those LIGO detects, filtering out everything from solar wind to the subtle thermal expansion of telescope materials. It's like trying to hear a pin drop on Earth while standing on Pluto with hurricane winds blowing in between. What's thrilling is how close we might be. The faint polarization patterns these waves could leave in the cosmic microwave background, the afterglow of the Big Bang, are already being hunted by telescopes at the South Pole and in space. A confirmed detection would do more than validate inflation. It would open a window into energies so high they unify all fundamental forces, realms we can't replicate in any particle collider. We'd effectively be reading the universe's birth certificate, written in the language of vibrating space-time. So while today's gravitational wave astronomy studies the crashes of black holes and neutron stars, tomorrow's might peer back to before time had meaning, to the instant when gravity itself first flexed its cosmic muscles. And hidden in those primordial tremors could be answers to questions we haven't even thought to ask yet. Floating astronauts and drifting water droplets might look like gravity has vanished, but the truth is far more fascinating. They're not beyond Earth's pull, they're surrendering to it completely. The International Space Station, orbiting 250 miles up, experiences about 90% of the gravity we feel on the surface. So why do astronauts appear weightless? They're not in zero gravity, they're in a constant state of freefall, a delicate balance where their forward motion perfectly counters Earth's tug, creating the illusion of floating. Picture throwing a baseball hard enough that its arc matches Earth's curvature. The ball would keep falling but never hit the ground. The ISS does this at 17,500 miles per hour, its crew perpetually falling around the planet rather than toward it. This microgravity environment isn't the absence of force but a perfect equilibrium, where everything inside the station, tools, food, even the astronauts themselves falls at the same rate, creating that iconic sense of weightlessness. Living in this relentless freefall reshapes the human body in bizarre ways. Without gravity's constant pull, muscles atrophy at alarming rates. Some astronauts lose up to 20% of their leg muscle mass during 6-month missions. Bones, no longer bearing weight, leach calcium into the bloodstream, weakening at a pace 10 times faster than osteoporosis back on Earth. Even the heart, freed from pumping against gravity, becomes more spherical and less efficient, while bodily fluids redistributed upward cause puffy faces and bird legs as blood pools in the torso. The station itself reveals gravity's hidden influence. Objects don't just drift aimlessly, subtle forces still tug at them. Residual atmospheric drag, pressure from sunlight, even the crew's movements create miniature gravitational disturbances. Astronauts have to account for these when conducting experiments, as molecular forces like surface tension dominate in ways they wouldn't on Earth. Water bubbles form perfect spheres, flames burn as blue globes instead of teardrops, and crystals grow purer without density-driven convection. This delicate dance has profound implications for space exploration. Prolonged microgravity could make Mars missions dangerous if astronauts arrive too weakened to work, prompting innovations like artificial gravity through rotating habitats. Even commercial research thrives here. Pharmaceuticals crystallized in orbit show promise for treating diseases, while 3D printed heart tissue develops more naturally without gravity's distortion. The next time you see footage of astronauts somersaulting through their spacecraft, remember they're not escaping gravity. They've become masters of it, riding a fall that never ends, where the rules of up and down dissolve into the ultimate demonstration of physics in motion. Pluto's gravity is so feeble that a person weighing 150 pounds on Earth would feel like a mere 9 pounds here, light enough to leap over buildings in a single bound and send boulders flying with a casual kick. This dwarf planet's pull is just 6% of Earth's, creating an environment where even the air behaves unlike anything in our solar system. Pluto's thin nitrogen atmosphere doesn't cling to the surface like ours. It expands and collapses dramatically with the planet's elliptical orbit, puffing up when closer to the sun's warmth and freezing solid onto the ground when it retreats into the distant cold. The numbers behind this weak grip are staggering. Earth's gravity holds onto our atmosphere with an escape velocity of 7 miles per second, but Pluto's is barely half a mile per second, so sluggish that nitrogen molecules constantly trickle away into space like sand through open fingers. New Horizons' 2015 flyby revealed the consequences. Vast plains of frozen nitrogen sculpted into polygonal patterns by slow-motion convection, where the icy surface churns like a lava lamp over millennia. Mountains of water ice hard as rock at these temperatures tower over the landscape, their sheer cliffs uneroded by wind or rain because the air is too thin to weather them. This feeble gravity also means Pluto can't maintain a sphere of influence like larger planets. Its largest moon, Charon, is so massive relative to Pluto that they orbit a shared point in space, creating a binary system that whirls like a wobbly dumbbell. Smaller moons like Styx and Kerberos dance chaotically around them, their paths tugged by this unusual gravitational partnership. On Pluto's surface, the effects are surreal. Charon looms 7 times larger in the sky than our moon, hanging motionless over the same spot while rotating once every Plutonian day. Yet for all its weakness, Pluto's gravity tells a story of resilience. Seasonal changes create temporary nitrogen glaciers that crawl across Sputnik Planitia, a heart-shaped basin filled with ice softer than candle wax under -400°F temperatures. The dwarf planet's interior might even harbor a subsurface ocean, kept liquid by radioactive decay and insulated by an icy shell. An underground sea defying expectations in a world where gravity seems barely present. What's most humbling is realizing how fragile Pluto's balance really is. If it were just slightly smaller, its gravity would lose all hold on an atmosphere, leaving it as barren as the Moon. Instead, it exists in a delicate in-between, a world with just enough gravity to tease out complexity, but so little that every feature feels like a whisper, a fleeting signature written in ice and gas against the void. Gravity doesn't just bend space, it moves through it at the universe's ultimate speed limit. When the LIGO detectors caught gravitational waves from colliding black holes in 2015, they didn't just prove these ripples existed, they clocked them traveling at 299,792 kilometers per second, the exact speed of light. This wasn't a coincidence. Einstein's equations had predicted it a century earlier. Gravity's influence isn't instantaneous but propagates as waves, their speed locked to the cosmic traffic law that nothing can outpace light. Think of it like watching lightning before hearing thunder. There's a delay between the event and when you feel its effects. If the sun vanished this instant, Earth wouldn't spiral away into darkness immediately. We'd keep orbiting the now vanished star for 8 minutes, the time light and gravity both take to cross the 93 million miles to us, before both its light winked out and its gravitational tether snapped. This cosmic synchronicity reveals a profound truth. Gravity isn't some magical, invisible thread connecting objects across space. It's a physical disturbance in spacetime itself, radiating outward at light speed like ripples on a pond. The implications reshape how we see the cosmos. When galaxies collide billions of light years away, their gravitational waves don't just tell us about the event, they timestamp it. The wave's arrival, synchronized with any accompanying light, lets astronomers triangulate distances across the universe with unprecedented precision. During the neutron star merger observed in 2017, gravitational waves and gamma rays arrived within 2 seconds of each other after traveling 130 million years, confirming their speeds matched to within 1 part in a quadrillion. This speed limit isn't just a rule, it's a cage for causality itself. Gravity can't convey information faster than light because doing so would break cause and effect, allowing paradoxes where events precede their triggers. Black holes test this boundary violently. When two merge, their final moments unleash energy equivalent to billions of supernovas, yet even that unfathomable power can't make gravitational waves cheat the speed limit. The wave's arrival time on Earth becomes a forensic tool, revealing how spacetime stretched during their journey and even helping test theories about extra dimensions. Yet mysteries linger. Why must gravity obey light's speed limit? At their core, both light and gravity are expressions of spacetime's geometry. Electromagnetism rides its curves while gravity is those curves. Their shared speed hints at a deeper unity, perhaps threaded through the elusive quantum gravity theory that might one day marry relativity with quantum mechanics. For now, every gravitational wave detection is a fresh reminder. Whether you're a photon or a ripple in spacetime, the universe enforces the same speed ticket, and no amount of mass or energy can buy your way past the cosmic patrol. The universe's ultimate fate rests on a silent, invisible tug of war, an epic battle between gravity's relentless pull and dark energy's mysterious push. On one side, gravity tries to hold everything together from galaxies to atoms. On the other, dark energy, the enigmatic force accelerating cosmic expansion, works to tear it all apart. The outcome of this struggle isn't just theoretical, it dictates whether the cosmos will end in fire, ice, or total disintegration. First, picture the Big Crunch, gravity's ultimate victory. If dark energy weakens over time or matter's collective pull proves stronger, expansion could reverse like a rubber band snapping back. Galaxies would rush toward one another, merging in violent collisions until the entire universe contracts into a single, searing point, a cosmic mirror of the Big Bang. Temperatures would soar to trillions of degrees, obliterating all structure long before that final singularity. It's a scenario where gravity, the force that built galaxies and stars, becomes the architect of cosmic annihilation. Alternatively, imagine heat-death gravity's slow surrender. If dark energy maintains its dominance, the universe will expand forever, growing colder and emptier by the eon. Galaxies beyond our local group will vanish over the horizon, their light stretched beyond detectability. Stars will exhaust their fuel, black holes evaporate via Hawking radiation, and matter itself may decay into radiation over uncountable millennia. Gravity will still operate, but its influence will be overwhelmed by the stretching of space, leaving isolated particles drifting in an infinite void where not even atomic bonds can cling together. But the most violent possibility is the Big Rip dark energy's brutal triumph. If it strengthens over time, expansion could accelerate so fiercely that it overpowers all fundamental forces. First, galaxy clusters would be torn apart, then individual galaxies. In the final months, stars and planets would rupture as space itself expands faster than gravity can hold them together. In the last moments, atoms would be shredded, then subatomic particles, until spacetime fractures completely. Gravity wouldn't just lose, it would be rendered meaningless in a universe where not even the fabric of reality remains intact. The deciding factor, a single number, dark energy's equation of state represented by the variable W. If W equals exactly -1, heat-death awaits. If it's greater closer to zero, gravity might yet prevail for a big crunch. If it's less more negative, brace for a rip. Current observations from supernova and the cosmic microwave background suggest we're on the heat-death trajectory, but the margin of error leaves room for surprises. What's haunting is how silent this battle is. Every second, dark energy creates new space between galaxies, while gravity works in the background, binding local groups and shaping structure. We don't feel it happening because the timescales are cosmic, but the universe is keeping score. And when the final tally comes in, it won't be a dramatic explosion or implosion that decides things, it'll be the quiet, inevitable mathematics of a contest that began the moment the first stars flickered to life. So while we marvel at gravity's power to shape planets and bend light, its most profound role may still lie ahead, as the universe's final judge, determining whether all we know ends with a collapse, a whisper, or a scream. From the silent grip keeping our feet on the ground to the cosmic collisions that shake the fabric of spacetime, gravity is the universe's ultimate architect and wrecking ball. We've journeyed through 30 mind-bending facts, uncovering how this invisible force bends light into rings around black holes, crystallizes dying stars into planet-sized diamonds, and flings entire galaxies across the void at unimaginable speeds. It's the reason Saturn's rings stay razor-sharp, why Pluto's atmosphere breathes like a living thing, and how a single teaspoon of neutron star material could outweigh Mount Everest. Gravity doesn't just rule, it reinvents. It sculpts the largest structures in existence, weaving galaxies into glittering webs billions of light-years wide, while also orchestrating the delicate dance of planets around their stars. It's patient enough to stretch Earth's days longer by milliseconds each century, yet violent enough to spaghettify stars near black holes in seconds. From the crushing grip of a white dwarf to the ghostly whisper of dark matter holding galaxies together, gravity's extremes redefine what we thought was possible. But here's the most humbling truth. Every fact we've explored is just a glimpse. the universe still hides gravitational secrets, primordial waves from the Big Bang, the true nature of singularities, and whether dark energy will eventually tear reality apart. That's the beauty of space mysteries. The deeper we dig, the more we realize how much we don't know. So which fact left you stunned? Was it the great attractor pulling thousands of galaxies toward an invisible horizon, or the cosmic slingshots flinging spacecraft across the solar system? Drop your answer in the comments. I read every one. And if you're hungry for more deep space wonders, hit subscribe. The universe has infinite stories left to tell, and we're just getting started. Until next time, keep looking up, because gravity's out there, rewriting the rules in ways we've yet to